Alright, so keeping on going. So sometimes in order to save my column limit, I do a whole bunch of defines and then undef them. So define it all, undef it all, alright? So if we go like here, let's make sure that everything lines up. And then in the exact same order too, so it's just really easy to like cut, paste, you know. But yeah, so you can see where those defines are made and where they are used. So this function right here, TAU001U32, that is my fetching function to find where that pixel is, get the location of this data, and load that pixel's data into a uint32. So it's going to take all of the individual bytes of the pixel, the A, R, G, and B, and it packs it back into a uint32 that I can manipulate. We kind of already went over that logic. I'm not going to go over it again. But basically, bit packing and bit unpacking, nothing too complicated. Unless you've never done bit packing and unpacking, then I guess it would be complicated because you've never done it. But, right, that's everything, right? I mean, everything is complicated until you understand it, right? Okay, so what else? So tile exponent, tile span, camera tile X, camera tile Y, the hot swapping index that locates the data that we're currently using, prefixed with EO2 for editor 2, because this does not mean that this memory location is hot swapped. It means it's the memory location that we are currently sampling from. So this identifies a certain 512 by 512 subsection of the master memory that we are currently sampling from within this shader. Whew, okay, so let's keep on scrolling down. So source and destinations below. So SD, 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 right? So, right, and I do this so I can easily locate stuff. So I'm going to highlight that, and we can just scroll, and we can see that it ends right here, and that is a lot, right? But at least we can easily scroll to identify that region. Okay, and then, right, we have subregions, right? So there's no actual scope that is telling me I must indent. I am just indenting for the goodness of indenting, right? Because it's going to make the code a little bit easier to read. You'll notice that I have a very short column limit and I over indent things. So, right, and so, okay, be up there, be up. Okay, so tacos, yay, alright. So let's keep on going. How much time we got? Okay, we just started this. Okay, so got more defines, tx, ty, so tile x, tile y, obviously. Looks like we're just converting these uint32 values into floats that we can work with a little bit better. Let's just clear our highlighting there and find tx and ty. We can make sure that those are different, right? So a little bit of static pattern analysis as we're reviewing this code, and we see equal amount of cyan and orange, and because I code in such a regular way, when I highlight stuff, I should always see some type of symmetrical or complementary balance in the code, right? So I see 4, right, symmetry, right? As long as there is symmetry or complementariness in the code, then I know there's not a bug in the code, right? So one of the reasons I write this code in such an OCD style is because I can look at the aesthetic of the code, and I can tell if there's a bug in the code because the aesthetic is incorrect. So I don't even have to logically analyze it to know if it's wrong. I can just highlight colors, and if the visual aspect of the code doesn't look right, then I know that there's a bug. You might say that is fucking insane. Maybe it is, but, you know, come on, halting problem, okay? You write tests to lower the probability that there is bugs in your main program, but then you probably have bugs in your tests, then you gotta write tests for your tests, and it's all a probability game, like, you know, if you're writing tests is good. I'm not saying writing tests is bad, because right, if you write enough tests, I heard you.
Okay, it's ready. It's getting cold.
Okay.
Steak, I don't want you to wait too long.
Okay. Okay, so when you write tests, the purpose of a test is to lower the probability that there's going to be a bug in the main code, right? And if you write enough tests, we could safely say for all practical purposes that there are no bugs in the code, right? But that cannot be said for the actual test. There's probably a whole bunch of bugs in your test code because your tests aren't tested. But that doesn't matter because you only care about the bugs in your main code. So you just barrage your code with tests, and eventually there won't be any bugs in your main code. Yes, there will be bugs in your tests because you have no test for your test, but don't worry about it because you don't want to go down that chain, right? Because halting problem, right? You don't want to write tests for your test and test your... You get the idea. Okay, so anyways. I guess the point of that was because of that paradox, I think there's a lot of value in the static analysis of the code and just having human eyes on that code that can do something useful. And if the code is all scattered and not organized, then the human eye isn't going to be very useful, now is it? So once again, rectangle source. Let's do the same thing here. So really quick, we notice a little bit of oddity here. So viewport 0, aka rectangle destination. Yes, that is true. And then we see, oh, there's a little assignment going on here. Now, why is this not colored? Okay, this is source and dest, and this is a different thing. Okay, so we got like 3 things here. Obviously this code isn't completely symmetrical visually, and that's kind of why we had this comment, which kind of makes it looks visually odd. The comment makes me know that, okay, everything's okay. So we're just taking our some of these so things were done in a slightly different order in the shader code than they were in the HTML code, because in the HTML code we actually have to set up the loop, and in the shader code we have no loop to set up, right? So we have a slightly different set of variables that we're starting out with, and the chaos here is just to get to a point where all the variables we need to work with are all ready for us to work with, right? We gotta so first we declare all our variables, then we get all of our basic variables ready to work with, and then we work with our variables. So we got 3 stages conceptually, 3 main stages going on in this code. But yeah, this here is kind of chaotic, right? Because notice the asymmetry here where the source is on this side, but then the destination variables are on this side, right? Complete chaos. But that's just that's the way it just had to be done. So I'm just trying to manage that chaos here before I get down here and start working with those values. So kind of try to manage everything, get everything in order before I start to do more intense calculations. So fragment chord X, fragment chord Y, right? GL frag chord. So viewport C height. And hold on. Yeah, because we've got the upper limit, the lower limit. We're going to minus them, and then we're going to add 1 because it's an inclusive boundary in my code. I always use inclusive boundaries. So the integer delta x. So not delta x in this case. Integer destination x, integer destination y. GL frag chord, right? We have texels that have a center point in the middle of the pixel. So if we want to get pixel coordinates, which I'm using, I'm thinking of everything as these boxes. When I think of pixels, I think of them as little boxes that are at finite points, and they don't actually have a width or height. Yet I draw them with a width or height. I don't know. Pixels are weird. But the way I think of pixels, I think of them as integer whole number coordinates, and they start at 0. So I just need to just subtract 0.5 to get that to all work. Also, I don't want to do... Pixels are... The math with pixels is all integer based, so... the conceptualization used in OpenGL for texels uses floating point. there's different models of pixels. They're both valid. They're both useful for different types of calculations. But in my case, I need integer coordinates, so we're getting integer coordinates. And then because GLSL is not very friendly to anything but floating point, we have the floating point versions of the pixel locations, and these are the pixel locations that are actually on the screen. That's why these are destination, right? Destination meaning the destination of the screen, also known as viewport 0. Okay, let's keep on scrolling. So we have a little comment here, right? So there must have been more, I'm going to guess, because I see a hashtag around this. So you see these hashtags right here. That usually means that this is like a footnote. So if we go Control F really quick, we can probably find a footnote. And there's no footnote, so what the hell? Well, I guess technically the footnote is, right here. Maybe I thought that it was important enough to not strip out the comment. Well, let's see what this is. Loop through every pixel of canvas instead of every pixel of destination viewport. Okay, yeah, so that is saying that every pixel of canvas means every pixel of the client. And that's what's going to be responsible for allowing us to draw a border around the image. Right, so we have this variable outside destination viewport, and I believe we kept that same variable name in the original code from the HTML. So let's go over here, and we see, let's scroll, outside destination viewport. So we kept the exact same variable name. So even though this is a very long variable name, which is kind of odd for me, if the variable isn't used very much, it gets a longer name, basically, right? And it's only referenced like 3 times in this code, so it gets a much longer name. Right, so my variables kind of follow the same kind of like frequency rules of a spoken language. The words you use quite frequently, participles, a, the, right, those are... They're short, right? Because you use them so much in speech. They're so high frequency that you keep them short, right? So same thing with my code. If it's high frequency, then I keep it terse. And the lower frequency it gets, the longer the variable name becomes. So outside destination viewport, and this is where we're drawing the border in the old code from the previous playlist. And now we have... okay, we got 64, 128, and 255. So, okay, that's red, no red, green, and blue. So the strongest is the blue, and it's right in the middle. So it's not dark blue, and it's not light blue. It's just like, it is in the middle in intensity. Technically, if you just have 255, that's like a complete pure blue. And then it's slightly desaturated, just slightly, with a 64. And so we got red, green. It's desaturated with... well, it's not really desaturated, right? Because you can't really desaturate until you get 3 channels working all at once. Because you have a smooth transition between here and here, which keeps you on that on the color spectrum without getting anything muddled. So basically what we have here is we have a somewhat darkish blue that is just has a hint of green in it. So it's subtly... It's mostly blue, with a little bit of hint of cyan in it, but like it doesn't actually look cyan. And I can prove that because we've already looked at it, right? So, yeah. So, right. Well, I don't know, maybe it looks different on your monitor. Okay, anyways, so, right, that outside destination viewport variable. And, so... The reason why I did this logic, I think I've described this before, but let me get rid of this coloring. The reason why this logic is kind of written in a backwards-ish way, where we're checking for if it's outside rather than if it's inside, is because the outside condition is very short. And so since the next condition is very long, we're obviously not going to accidentally miss this case, right? Because this case has a lot of code in it. But if we had flipped this around the other way and had this case at the end, right, it would be very likely that we could, if we're scrolling through this code, that we would miss this case, where we would only see the outside destination viewport. Like if this were inside instead of outside, right? If inside, right? Well, then if inside and if well, I guess it doesn't have to be flipped like that. But I don't know. The idea is just to get if you have two branches, you want the branch with the least amount of code to be first, just so that you don't accidentally miss it when you're looking through the code. That's the point here. So the ordering is very intentional. Like, as far as the verbiage, I'm less concerned about the verbiage than about making sure that this shorter block of code comes first. Because I know some people, because I had a boss once who was always like, don't have weird variables that say, if false, right? Like have a if true, right? Like have an if set, not an if unset, right? Don't use negatives in your speech. Oh God, negatives are so much harder to understand, so only use the positive phrasing of something, right? Yeah, I get that. I get that where that comes from in psychology. Because as a kid, like I remember being a kid and like not being able to understand the sentence, I am not a horse. Because it's like, I am not a horse. What is a not a horse? What's a not a horse? I don't know what a not a horse is. I am not a horse. Wait. I am not a horse? So I am, and not a horse. That would be like so that's like saying I am car. I am not a horse, right? So I get where like when you're not used to language, that having those negations in language can make things more complicated to understand. And even as you mature and have a better grasp of the human language, that still is like an extra computation. And so I do get that it is extra processing. We're going to say that extra processing does not matter, because being able to spot this and not miss this is a lot more important than worrying about the weird oddities of negation in language. Where are we? We're at 18 minutes. Okay, let's keep on going. So, if 0 equals outside destination viewport, right? Weird wording. Basically, if we are inside the viewport, right? So yes, I've decided to go with some weird wording because we're not. I wanted this block down here. That's basically what happened. Okay, enough justification. Okay, here I am justifying myself. Okay, so the width and height of viewport 0 and viewport 1. Viewport 0 is the destination viewport, the on-screen pixels. Viewport 1 is the actual data we are going over. So I'm just highlighting those sections really quick. Make sure we don't have anything out of balance there. LDX and LDY is the local X and local Y. So if we take a look at that right now, okay, we see that is balanced, and we see that we're just subtracting the origin. So basically we're doing a global to local calculation here, and that is going to be needed for mapping the internal tile coordinates, I believe. Or maybe not. So let's see what we got here. So source X and source Y. Honestly, I already figured out these formulas previously, and I know they work. But I am not good enough with math to honestly be able to just look at this and be like, oh yeah, that makes obvious sense. maybe if I do these formulas more often, it'll make more sense to me and become more natural. But these formulas are definitely not natural to me, right? Like I've solved it algebraically. I can set up the formulas. I can solve the formulas. But I cannot just look at this formula and be like, oh yeah, that makes perfect sense, right? So, knowing that this is source X and this is source Y, that's the important part to me. Knowing that I have meticulously checked these formulas is important to me. Am I a little bit scared that I don't understand these formulas right away just by looking at them? Yeah, that does bother me. That definitely bothers me. Um, but the only real thing you can do is you check your math, and hopefully after writing enough formulas that involve this sort of logic, eventually, hopefully, I will just get the hang of it. But for now, I solve everything algebraically, I test it out, make sure it works, and then I just use it, right? And so this is a transcription of the logic we solved in the previous tutorial or playlist, right? So if we go through here, we can see it. Let's clear these flags here. So the formula, this formula here, these blocks of formula are the ones in the code we're using right now. So, right, we wrote the code for the canvas in a slightly strange style because I knew I wanted to eventually bring it over to a GLSL shader. And so here we are, just taking it directly and just pasting it right in there, and it works like a charm. And that's one of the nice things about being very consistent with how you write your code, because I just could cut and paste and I didn't have to rework anything, right? And the less you have to rework, the less likely you're going to screw something up. Okay, so tile internal coordinates. Should I go over this? So local SX, local SY. Same thing with SX. Okay, the origin. So this is just getting SX and SY to start at 0, because SX and SY are locations. Right now, SX and SY are locations within your viewport, viewport 0, which is the on-screen viewport, which is a subsection of the client rectangle. So these locals are just getting it so the first used value of these is going to start at 0 rather than starting at whatever the inset for the viewport is. That's what this is, right? So rec source, source is, why is source, that's VP1. Oh, sorry, I'm mixing up my viewports. I was just talking about the destination viewport. Source is the off-screen data. But similar concept, right? The source X and source Y coordinates are all within the bounds of this rectangle, right? And this rectangle may not be at 0, 0. So this is just making sure that the first SX and SY starts at 0, 0. And why I need that, I don't remember why I need that, but I guess I need it. And I can see why I need it down here, but let's keep on reading. So tile internal coordinates. This is where we get the calculations needed for shading the inside of every single tile, and it is also the math we will need if you want to blit images to those tiles. So we got some little notes here. TP0 width, TP0 height. We already went over what that meant, but we can do it one more time. So this is a tile measured in pixels within the context of viewport 0. So as seen on viewport 0 is the destination viewport, so it is what is on screen. So basically it's saying, here is the size of a tile as seen on the screen. And so it's important to distinguish between the different spaces, right? Because the size of a tile on the actual data is just 1 pixel by 1 pixel, right? Because that's all you need to encode the tile value. Notice that there is some weirdness going on here. We got this NX and NY. That's because if we wanted to use groupings of, say, 4 tiles to encode a single tile value, then nx and ny would be a value other than 1, but right now it's just 1. So we're just dividing by 1 and we're not actually changing this. But I just left that in there because I thought, oh, maybe I'll want to add that feature later. Let's just put the math for it in there just so that it's easy to shove in there later if we want to. We won't have to rework things as much. So these values, they look like bounds values. So there is a prefix on all of these, and then the suffix, right? So x0 and y0 is where things are starting. And that was a bad highlighting job. Let's try that again. So let's highlight the beginning with one color. Let's do x0 with another color. Let's keep the y. I only have so many colors I can use to highlight. So let's so we got the zeros, we got the ones. So lower bounds, upper bounds. The lower bound is always 0 because the tile coordinate, the local coordinates of the tile, right? They're always going to start at 0, 0. Right? So that'll make it easy to map an image onto the tile, right? Because they have the same origins. So then the x, so this is the x and y value within this range right here. So right, so we have a for loop between x0 and x1 and y0, y1, right? We got two loops nested inside of each other, iterating through all the possible coordinates that are tinco x and tinco y for tile internal coordinates x, y. And then here's the formula for that. I'm not going to go over the formula because I already wrote it in the previous tutorial, and like I said, it's not completely what do you call it? Second nature to me. The formula is not second nature to me. You know, I solved it. It works. Good enough for me, right? I solved it. It works. And, I mean, there's one thing. Checking for consistency, right? So, like I said, we can highlight the SX, SY, right? And just make sure we have balance. And as long as everything looks symmetrical or complementary, then I'm good, right? I have seen it work. Everything looks symmetrical and in order. I'm satisfied. So gradient mapping calculations. And so, right, the first thing we do is we get the distance from each individual edge. So we take a pixel within a pixel x, y, within the local boundaries of the tile. And these are the local boundaries here. The minimum and maximums on the x and y. And we're going to take the x, y's distance from the left edge, right edge, top edge, and bottom edge. And then we want to filter down and figure out which edge are we closest to, and we will use whatever edge we are closest to calculate a gradient color. So really quick, if we go over here, so notice that right, we're closest to this edge here, and that's why we have a dark color, right? Because how close you are, the closer you are, the smaller of a number it is, right? And so that's why we get darker along the edges. And so if you're right over here, okay, we're this far from this edge, this far from this edge. Oh, but we're really close to this edge, and we're really far from this edge. So we're going to use the distance from this edge to color, and that's why the gradient is the way that it is. I did a bad explanation there. Maybe that made sense to you. I'm sorry if it didn't. But anyway, so you take the distance from the left edge, the right edge, the top edge, and the bottom edge, and then you're just going to filter them down. So you see right here, we're going to sort the left and right into an x variable and sort the top and bottom into a y variable. So let's take the x and the y and see what we do with that. Oh, and then we take the x and y and we filter it down one more time into a variable that is one-dimensional and encompasses the minimum of the x and the y, and then we will normalize that variable. And notice that I have a times 4.0. If we wanted to use a proper range, we would use 2.0, right? Because at most you can be half the distance. all right, because if we're in the center, that's the largest value, right? Because the distance from the left to the right, this whole distance will never be used. The biggest value you're ever going to have is right in the center, which is half, right? So to get the full color range, you need to multiply by 2 to make up for that fact. And I'm using 4.0, and that overblows it a little bit to make it a little bit more flat on the top, instead of making it like a complete pyramid shape. So should I document that anywhere? Yeah, I don't care. God, there's so many comments in here. Yeah, it's a magic number. Yeah, that's kind of bad. Maybe I'll hate myself for it later. I don't know. I'm not going to document it. Okay, now I have to. Normal. Let's say 2.0 pyramid. I'm going to say 2.0 is a pyramid, and then we're going to say 4.0 overblown flat top. Oh boy. Obviously that's kind of cryptic, but it's enough to where, you know, if I'm trying to figure it out, these comments will make me figure it out a little bit faster. After I've a year later, after I've not remembered what that does, this will help me refigure it out. Sure. Okay, so die base. Why die? Because I like things clustered in groups of 3, and RGB is not technically correct because it's RGBA, but then that's 4 letters, and OCD. That's basically why I'm using the word die, right? Tie-dye, right? BAS for base. So this is the base color. The base color is just whatever the color of the pixel is, right? So we're going to sample the source material, right? The off-screen VRAM. We're sampling the texture at these coordinates, and this texture sampler function has the ability to sample from different hot swapping rectangles, and the hot swapping rectangle we will use is specified by this uniform here. And then after we have the base color, and yeah, we have a little shouty thing here because I screwed this up, but this is already declared further up in my shader code, and if I redeclare it, I shadow variables, and then everything on the screen ends up being white, and I have no fucking clue why. So yes, this does actually warrant a big shouty message, because if, like, I do not want to make that mistake again, and as I rework things, it will be very easy to be like, oh, hey, this doesn't actually, oh, where did I declare it? Oh, it's not declared anywhere here? Well, it's way up here. It's so far up there that right, you miss it, right? Because, or actually, is that in a different shader? Hold on. UVec4, well, it's in a different scope, right? So it doesn't get caught as being redeclared because it's in a different scope. And then if you declare it in this scope, then the change won't persist when you get outside of this block of logic. So anyways, you take that base color and you just multiply by that normalized color for the rectangular gradient intensity. So if we go over to TED Nor, right? So tile edge distance and normalize. So we can go up here and see that it's within the gradient mapping code right here. And so that's all you need for getting those gradients. Then I have a little air checking here where I just paint a red color onto the screen if for some reason the tile span variable has not been set, because I ran into that problem while I was coding. And then this is the this is my output frag. It's pixel fragment. I forget what you have to call it in the actual shader code, or if you have to define your own. This might actually be an out variable, because we're using WebGL2, and so the new shader syntax has input and output variables rather than using hard-coded constants like glfragcord. glfragcord is obviously still here, but other things that would be varyings are now either input or output variables, whereas a varying is varying is a less specific specifier than in and out variables. In and out variables is like a subset of varying, right? So in variable is a varying that is input, and then an out variable is like a variable that is a varying that is an output. I'm not the best teacher here. Yeah, so then we got some empty slots, and these are for the different editors that do not exist yet, right? So the shader code for editor 3 does not exist, but we have the slot for where that code would go. Editor 4 does not exist, etc. All the way up to 9. What do we do when we run out of digits? That'll be a bad day, because I'll be happy about it in one aspect. Oh god, 36 minutes. I'm going to stop recording. We're done here.